Okay, hello everyone. So in this video I'm going to teach you give you some examples about digital CMOS circuits so that you can make use of these examples to understand the basic concepts of how we implement digital logic gates using CMOS, complementary CMOS circuits. Okay, so I'm going to assume that you guys know these basics and then build on top of that. What are these basics that I'm going to assume that you know? The NOT gate is implemented by two MOSFETs. One of them is a PMOS and the other one is an NMOS. And I'm going to assume that you know that the output is the complement of the input, and you know that how this gate operates. When A is 1, then this is off and this is on, and thus the output Y is equal to 0. Okay? Output Y is equal to 0 when A is 1. Okay, but when A is 0, so this is when A is 1, okay, Y is equal to 0. Why? Because this is on, because this is off, and this is on, and thus the output is connected to Y. And when A is 0, then Y is 1. Why? Because when this is 0, then this becomes on, and thus the output is connected to the VDD, and thus the output Y is equal to 1. Okay? So, what else am I going to assume? I'm going to assume that you know that the PMOS has two ways of drawing the circuit. Either you draw it using this way, or you draw it using the bubble which is mentioned at the gate. Okay, so that's the PMOS. And if I want to draw the NMOS, then I draw it using this, any of these two ways. The one that we're going to use regularly is this, these two methods. Okay, these two methods are the ones that we're going to use in CMOS when we draw a CMOS integrated circuit. Okay, and if I want to have the PMOS to be on, then I need to feed here a 0 and connect this source to the VDD. Similarly, if I want the MOSFET to be off, off means that it is not on, it is, you can basically throw it away. It is basically disconnected. That's basically the concept of off. So as if you do not have any transistor at all. Okay? And if you want this to happen, then you connect VDD at the gate, and thus the source to the gate is 0, and thus it is not exceeding the absolute value of the threshold voltage, and this is why it is going to be off. Okay? So, similarly, for the NMOS, if you want the NMOS to be on, you need to connect a VDD at the gate, and the source has to be connected to the ground. Okay? And this is why when, and oppositely, when the NMOS needs to be off, when you want to put and make it an off gate, then you connect a 0 to the gate, okay, and connect the source to the ground. Okay? Some basic digital design fundamentals that we have in this, that we're going to use, is that if I want to put a literal A, a variable A, or if I want to claim that A is 0, then I write down A bar. It shows up as A bar in the equation. Okay? And if I want to claim that A is 1, then I use the variable without a complement, without a bar. Okay? And also you might need the De Morgan's law. What does De Morgan's law say? It says that if Y is equal to A plus B whole bar, then you could let this bar be distributed over the two variables A and B. But you have to convert the plus sign to a multiplication. The OR gate, you have to convert it to an AND gate. Okay? Similarly, if X is A multiplied by B whole complement, then you could distribute the complement between the A and the B, and thus you need to convert the B to you need to convert the OR gate, the AND gate to an OR gate. Okay, so these are the basics that you need to know by heart. If you do not know them, there you go. These are the ones that are that you will use in any if you want to answer any of the CMOS circuit questions that you might see in an exam. And these are pretty much like worldwide conventions. Whatever university you are in, whatever class you are in, these are most likely you're going to be using these circuits for these concepts for the CMOS digital circuits. Okay, so let's begin. So right now what I'm going to teach you is how to design equations, how to design logic gates which have some sort of operation using these CMOS circuits. Okay, so let's imagine that we have a gate performing like this. Okay, and this is a PMOS gate. This is a PMOS transistor. Okay, and you have the other part of the gate which is an NMOS. Okay, and I'm telling you that I'm feeding here an A and here a B, and I'm taking the output Y from here. I'm feeding here an A, feeding here a B, and this is VDD. Okay, and I told you that the output Y is A, okay, plus A bar plus A bar and B bar. Okay. Let's first know, in order for you to know how I got this equation, let's first know what do these represent? What is this gate? What is this circuit doing? First of all, you need to know that this circuit, any circuit in the digital complementary CMOS integrated circuits, you have to know that there exists something called the pull-up network and something called the pull-down network. You know that the benefit of digital CMOS circuits is to design an equation that takes either a value of 0 or a value of 1. So you know that the Y is going to be either VDD or is going to be the ground. Okay, and if those inputs happen to have some sort of value that makes Y equals to 1, then this one comes from the VDD, which means that this network is on and this network is off. Because if this network was on, then in that case, Y is going to be equal to the ground. So I want to design, and it happens that this is really the case. It turns out to be the case that when A and B both are zeros, this network is going to be on, which means that this transistor is conducting, while this network is totally off. Okay, so you pretty much can take it off the circuit and erase it at all, totally. Okay, so that is the case if A and B happen to be zeros. And that's why I know that the Y, output Y, is equal to A bar multiplied by B bar. You do not know how I got this equation, but I'm telling you that this is how this circuit is going to operate. And I'm going to teach you later on how we can get this equation. Okay, so what do we learn so far? We know that this is A and this is B. This is called the pull up, the pull up network, and this is the pull down network. Okay, why is it called pull up? Because it connects the Y to the VDD. It pulls it up. It pulls its value of the voltage up if it is on. And why is it called pull down? Because it pulls the output Y to the ground whenever it is on. Whenever it is on, this value of Y is connected to the ground, and thus it is the output Y is pulled down. So you have a pull-up circuit and you have a pull-down circuit. Since you expect that the output is going to be either 0 or a 1, you know for sure that it is not going to be always 1, and you know for sure that it is not going to be always off. It will depend on the values of the inputs A and B. Then you expect, in any circuit, to have a pull-up network or a pull-down network, and a pull-down network. You do not expect to see only one of them. If I draw only one of them, then this is wrong. I have to draw the other circuit. I cannot draw one of them and connect this to the ground, for instance. This is not feasible. This is not correct. Okay? So in any circuit, you expect to see a pull-up circuit and you expect to see a pull-down circuit. Okay? So that is the first concept. You expect to see a pull-up circuit and a pull-down circuit. What's the second concept? The second concept is that you need to know that if you have these in series, then you expect to see them in the pull-down network in parallel. Conversely, if you have these in series, you expect to see them in parallel in the pull-up network. And similarly, if I draw a gate where you have a bunch of series transistors in the pull-up network, then you expect the pull-down network to be the opposite. You expect it to be, this is A, this is A, this is B, okay, and this is B. This is connected to the ground, and this is connected to the VDD. Okay? You expect to see, if these are parallel in the pull-up, then you expect them to show up in series in the pull-down network. Okay? And this is pretty much a constant factor, like something that is a constant over all a constant fact over all the digital CMOS circuits. If you have a bunch of gates that are in series, you expect them a bunch of transistors that are in series in the pull-up network, you expect them to show up as in parallel, as in series. If they're in parallel, they become in series. If they're in series, they become in parallel. So pretty much you can detect, if I gave you only the pull-up network and I ask you to please draw the pull-down network, then you could deduce the pull-down network from the pull-up network. You cannot say, yeah, but I'm not given the pull-down network. Perhaps it does not look like this. Well, if it does not look like this, then it is not going to operate this way. If I want this circuit to operate in a way where it implements this equation, then I have to see some sort of symmetry between the pull-up and the pull-down. Why? Because when this A and B are on, the only way for this, okay, so when the pull-up network is on, I have to have this pull-down network is on. And for me to have this pull-down network is on, if they are in series, then this has to be in parallel for the pull-down network to be off. So if this is on, this has to be off. And if this has to be off, then this has to be the opposite way. If these are in series, then these have to be in parallel so that these become off. Why? Because if this is 1 and this is 1, then you have this is on and this is on, and this is on. And in that case, this is going to be, so if this is 0 and this is 0, this is going to be on and on. Okay, so I put here A equals 0, A, B equals 0. Then in that case, this is going to be an on and this is going to be on. Okay, and similarly, since this is A, so they are basically connected together, but I didn't draw the line just for simplicity. Okay, then thus this A is going to be 0 and this B is going to be 0 as well. Okay, and if this is 0 and this is 0, then this has to be 0 and this has to be 0 as well. So this becomes off and this becomes off. When you connect a 0 to the gate of an NMOS circuit, then an NMOS transistor, then you expect that this NMOS is going to be off. Okay, so you have this has to be off and this also has to be off. Okay, so the bottom line, when you have series, then you have parallel, and when you have parallel, you have series. And this is why in the exam I could give you a network, either the pull-up or the pull-down, and I ask you to give me draw the second half, the other half of the network of the circuit. Okay, so you can pretty much deduce this, and we're going to solve some examples on that. Okay, that's the second one. So the first thing is that you have two networks. Okay, and the second fact is that you have, and these two networks are the opposite, are complementary, are dual to each other. One of them is series, then the other one has to be in parallel. If some of them are series and parallel, then this is going to be parallel and series. And we're going to take an example on that. Okay? So, the third fact that you have to know is that the pull-up network is always a PMOS circuit. So I do not expect you to draw, if I ask you to draw the pull-up network, please do not forget the bubble. If you draw it without a bubble at the entrance at the gate, then this is an NMOS circuit, and it is very wrong. It is totally incorrect to draw a circuit, or a pull-up circuit that has an NMOS in it. It should be PMOS. Okay, that's a fact. Okay, and similarly, the pull-down network is always NMOS. So this is always NMOS, and this is always PMOS. Okay. So now, if I give you, let's solve an example. I give you a network like that, this is VDD, and I gave you that this is working like this, okay? B and C, okay? And this is A. So is this the pull-up or the pull-down? Well, the pull-up is always connected to the VDD, and the pull-up always has a bubble, has a PMOS circuit, has a PMOS transistor. So this is always going to be the pull-up network, okay? Does this work by itself? Of course not. And this is why I'm drawing some dots here. Why these dots represent that there exists a pull-down network complementary to this pull-up network, okay? And I'm asking you, please draw the pull-down network associated with this pull-up network. Well, you expect to see something, a dual, something complement to that, okay? So, you expect, let's have a look here. We have this is in parallel, is in series with this gate, so I expect to see them in parallel in the pull-down network, okay? So let's draw them in parallel, okay? So I expect something to be here and something else to be here. Why? Because these two are going to be in parallel. These are in series, then these two are going to be in parallel. And then at the end, I expect to see the ground here. Okay? So let's draw the first one and the second one. Okay? The first one is A. Okay, so let's draw the A. And it is an NMOS. The second one is this circuit. I'm going to draw this circuit here. But remember, I have two transistors in this pull-up part of the circuit. In this circuit, I have two transistors. And they're drawn in parallel. So I expect to have them to show up here in series. Okay? So these two are going to be drawn here, but they're going to be drawn in series because they have already showed up in parallel in this network. Okay? B and C. Okay? And remember that this is NMOS circuits, and this is why I did not draw a bubble here. If you draw a bubble here, then this is a PMOS, and this is totally wrong. Okay? Whatever is PMOS, whatever is PMOS here, the opposite here has to be NMOS. And there is no pull-up network that has an NMOS. Okay? So and this is basically the output Y. Okay? You do not know what the output Y is, okay? But still you were able to draw the pull-down network from the pull-up network. What if I gave you the pull-down network? Can you draw the pull-up network? Yes, you can. How? You basically look at what is in parallel and draw it in series. So let's write down an expression for the output Y. Okay? What is the output Y in terms of A, B, and C? Well, you can take either the pull-up network and try to use it to write down the output Y, or you could make use of the pull-down network. You do not have to look at both of them, because basically both of them are dual to each other. Okay? So, we're going to make use first of the pull-up network, and then apply the same concepts on the pull-down network, and see if we really reach the same expression or not. Okay? So, from the pull-up network, Y equals. When is Y equals to 1? Well, the pull-up network is the main benefit of the pull-up network is that it lets the output Y to take the value of 1, because the pull-up network pulls up the value Y. So when does the pull-up network lets the value of Y equals 1? When the pull-up network is on. So you have to have this on, so you have to have this on, and this to be on in order for the Y to be connected to the VDD. Because if, let's say, if this is off, if this was off, if the value of A was such that it makes this off, then you expect that the Y is not going to be connected to the VDD, even if B and C were taking values that make these two transistors on. Okay? And similarly, if this network is on, if this side of, if this part of the pull-up network is off, and this is on, then you definitely guarantee that the Y is not going to be connected to the VDD. Why? Because this is off, but this, although even if this is on, there is no connection. These are off, which means that you can remove them from, they're basically an open circuit. Okay? So in order for the pull-up, for the Y to be a value of 1, the pull-up network has to be on. So the on has to come from this this upper transistor, or from this one or that one. So what do I mean by that? So you need to have transistor A, which is QA, has to be on, okay, and any of these two has to be on. QB or QC has to be on. Why? Because let's assume that this, not both of them are on, just one of them is on. Then you expect this is on and this is on, so you expect that the Y is going to be connected to the VDD. So not both of them have to be on. One of them is sufficient. But when they are in series, both of them has to be on, otherwise one of them, if one of them is off, it's going to open the circuit. So when they're in parallel, you do not really care about which one is on. Only one of them is sufficient for us to be on. And this is why you write it down in this form. QA has to be on, and one of these two, B or C, have to be on. Okay? Okay, let's write down when is QA on. When do you expect to see A to be on? Well, in order for A to be on, then this transistor has to be on. And in that case, this is a PMOS, so you have to have here a voltage potential difference. So this has to be 0. Why? Because if this was not 0, if this was 1, then there is no potential difference at the gate to source junction. And this is why you do not expect this to be on. You expect it to be off. So A has to be 0, which means that A is 0, so I write down A bar. Okay? A is 0 means I write down A bar. Okay? Multiplied by B or C. This has to be on, which is QB, plus QC. So either this on or this on. So how do I make the QB on? How do I make the QB on? I make the QB on by forcing this value to be 1. Why is this value going to be 1? Well, I have to have a potential difference here, which means that this has to be 0. Because if this was VDD, then I definitely guarantee that this is not going to be, this junction between the gate and the source is not going to be on. Okay, if this is VDD, then it is not going to be, its potential difference is 0, and thus it is not exceeding the threshold voltage, and this is why you expect that this transistor is going to be off. Okay, so that I need to have this B to be a 0 in order for this transistor to be on. So, do I guarantee that this is going to be VDD? Well, yes, because this is, when this is on, then you expect that this value is going to be almost VDD, or VDD minus a very small value. So this is expected to be VDD. And that's why you have to have this value close to 0, so that this potential difference becomes VDD, and thus this becomes on. And since I want B to be 0, then I write down B bar. Okay? Similarly, it is going to be C bar. So this is the expression for Y. If I write it down from the pull-up network. Okay? Let's write it down from the pull-down network without making use of this equation. Let's try to find the value of Y using the pull-down network. Okay? So what does the pull-down network do? The pull-down network lets Y become a 0. It pulls it down. Okay? So I need to find the value of these transistors. When are they on and off? When are they on and off in order for Y to be a 0? When is Y a 0? y is 0 when the A is on, so that, because when the A is on, the y is connected to the ground, or when these two are on. Okay? When these two are on. So in order for me to write down an expression for y, okay, I need to have this on or these two on. Okay? But remember, we're not writing down an expression for y, we're writing down an expression for y bar. Why is that? Because I'm looking at the value of A and B that makes y equal to 0. When we're looking at the pull-down network, we want y to be 0. And y is 0 is represented by y bar. Here we're looking at the pull-up network, we want the value of y to be 1. And y equals 1 means that we write it down, we write the variable y as y, not y bar. Okay? So here we're looking at the value of y bar. Okay? So when is y equal to 0? Y is equal to 0 when this is on or this is on. They do not both have to be on. This side and this side do not both have to be 1. Because if one of them is on and the other one is off, I definitely guarantee that there will be a connection from y to the ground. Okay? And that's why the y is going to be equal to 0. Okay? So either QA is on or QB and QC, both of them are on. Both of them are on. Okay? So remember that this is not really an expression for A and B. QA and QB and QC, where when I write them like this, that's just my personal convention. Okay? It means that I want this to be on, this to be on, this to be on. I'm basically writing down here whatever that needs to be on. Okay? I do not have, I'm not really indicating that this is a value of A or A bar or whatever. Okay? So this is basically just to let me know that I need this to be on, this to be on, and this to be on. So that it can help me in writing down the equation in terms of A, B, and C. Okay? And this is why I should not write an equal sign here. I should write down an arrow. Okay? So it is not an equal sign. Okay? So here y equals 1 when, okay, QA is 1 and QB or QC, any one of them is on. Okay? And here, and thus we can deduce that y equals to this value. Okay? So y is 0 when QA is on or QB and QC are on. Because if one of them is not on, if one of them is off, and QA is off, then you definitely guarantee that this is not going to be on. You guarantee that it is off. Okay? And the y will not be connected to the ground. Okay? So you want either this branch to be on or this branch to be on. Okay? So how is the branch on the left on? How can I make this on when the A is 0, is 1? Okay? So let's write down the y bar first. Y bar, because it's y equals 0. Okay? Okay? And then I need this value to be on. I need this transistor to be on. How can I make an NMOS on? Its source is connected to the ground, so the A has to be connected to VDD. Okay? So I write down A or A bar. I need to write down A. Why? Because I need to make A equals 1, which is A equals to the VDD, so that I can make here a connection. I make here a potential difference, and thus this becomes on. Okay? Plus QB, QC. Okay? So I need to have this on and this on. So in order for this to be on, this has to be 1. In order for this transistor to be on, this C has to be 1. So B, C. Okay? BC. Okay? So that is the expression from the pull-down network. Is this expression equivalent to that? It turns out to be the case. Do you want to prove it? Let's prove it using De Morgan's law. Proof. Okay? I'm going to take this and try to convert it to that expression. Y bar equals A plus BC. Okay? Y equals A plus B, C, all bar. I take a complement to both sides, okay? And then Y equals, apply De Morgan's law, A bar multiplied by B, C, all bar, okay? De Morgan's law, when you apply the bar to both terms, then the plus sign is converted to an addition and the bar is applied to each term alone, okay? So the plus sign is converted to a multiplication, and then the complement is divided, okay? So which is equal to A bar multiplied by B bar plus C bar. Why is that the case? Because De Morgan's law applied again, you find that B bar plus C bar, okay? And the ANDing is converted to OR gate, okay? Which is equivalent to that, okay? Which is equivalent to that, right? So whether you have the pull-up network or you have the pull-down network, you can deduce the pull-up from the pull-down or the pull-down from the pull-up, or you can deduce the equation from this pull-up or from this pull-down network. So you might ask, yeah, okay, if I was given the pull-up network and I asked, if I was given the pull-down network only, and I was not asked to write down to draw the pull-up network, can I deduce the equation alone? Yes. Shall I need to leave it on this form or in that form, convert it to that form? No, you can leave it on this form. This is a correct form as well for the pull-down network. Okay? So let's take another example. Okay, let's draw here the pull-down network. This is A, B, C, D, E, and F. Okay? And the output Y is here. Okay? This is a pull-up or a pull-down. Well, definitely, since it's connected to the ground, then it is a pull-down. Since it's NMOS, then it is a pull-down network. Okay? So the question is, I want to find out what the value of Y is in terms of A, B, C, D, E, and F. Okay? And in addition to that, after that I want you to draw the pull-up network. Okay? So let's first find the value of Y. Okay? In order for Y to be a 0, why am I asking myself what is the value of Y equals 0? Because why am I asking myself to find the value of Y, to find the network when the value of Y equals 0? Because it's a pull-down network, and the pull-down network allows the circuit to be pulled down, means connected to the ground, so I need to look at the value of Y equals 0. Okay? When is Y equal to 0? When there is a path from Y, which is the output, to the ground. When is there a path? When QA is on, because if QA is off, then we're done. Okay? When QA is on, and this network is on, regardless of how it is, regardless of how it looks like, it has to be on, okay? Because if it is off, then I definitely guarantee that there will be no connection from this node to that node to the ground, okay? And QF also has to be on. Okay, so F has to be on, A has to be on, and the network, the whole network has to be on. Okay? The whole network, the whole middle network, this has to be on. Okay, when is this whole network is on? When there is a path from this part, from the B transistor, or there is a path from this side. So when QB is on, or this side, this branch is on. When is this branch on? When QC is on and this branch, this whole middle network is on. So it is an AND. Okay? So when is this on? When this QD is on or the QE is on. Okay? So again, so if I want the Y to be connected, Y equals 0 to be connected to the ground, then the A has to be on, the F has to be on, and this whole network has to be on, which is represented by this term. When is this term on? When this branch is on, or this branch is on. So QB or this branch. When is this second branch, the right branch, is it on? It is going to be on when this QC is on and QD or QE, any of them is going to be on. Okay? So we write down Y or Y bar is equal to A, okay, YA, because if I want this QA to be on, then A has to be 1. If I want QB to be on, then this has to be 1. This has to be 1, this has to be 1, and this has to be 1, this has to be 1. Okay? So you expect all of the variables to show up as non-uncomplemented variables. Okay? So B, okay, plus C multiplied by D plus E, all multiplied by F. Okay, and this is the expression for the pull-down network. Is it the same as the expression for the pull-up network? It is not the same, but it is equivalent to it. Okay, if you want the pull-up network, the expression for the pull-up network, then you take a complement to both sides and apply De Morgan's law recursively. Okay, so right now let's figure out what the pull-up circuit looks like. Okay, and I'm going to draw this because it's going to take some space. So, what do we have? We have 3 series terms. 1, 2, and 3. Okay, they're in series, so I expect them to show up in parallel. Okay, so I expect this to show up in parallel. That's the first one, that is the second one, and that is the third one. 1, 2, and 3. Okay, what is the first one? The first one is A, so let's draw the A. And after that, of course, I expect to have something to be connected to the VDD. Okay, so let's draw the first one. The first one is A, which is, I expect to have a transistor here, and do not forget the bubble, because it is a PMOS, okay? And then connected to the A, to the VDD, okay? The last one is the F, and it is connected to the VDD as well. Okay, and let's have a look at the middle one. This is the F, and this is the A. Okay, and let's have a look at the middle one. What does the middle one look like? We have the middle one. It has 2 branches, and both branches are parallel to each other. So I expect them to show up as in series. So I expect to see something here and something here. The first one is the B, and the second one is the CD and E. Or the first one here is the B, and then this is CD and E. So it doesn't matter which one, because they're in series. It doesn't matter. Does the B show up or show down? Okay, so I'm going to choose that it's going to show down, show up here at the very bottom of the circuit. B, and then I expect to see this part here. What is this part? This branch is equal to C in series with D and E. Why is it in series with D and E? Because this is in series with that. Okay? So I expect them to show up in parallel. Okay? So let's let them show up in parallel. So 1, 2, and then connect it to the VDD. Okay? So the first one is the C. It doesn't really matter whether you put the C on the right or on the left, but the most important thing is that it is a PMOS. So you need to draw the bubble. Okay? And then connect it to the VDD. Okay? And then we have the D and E. D and E are in parallel, so I expect them to show up in series. Okay? So this is how I'm going to draw them in series. This is the D, and this is the E. Okay? So, again, 3 branches in parallel, 1, 2, and 3. Why in parallel? Because they show up in series. The first one and the last one is A and F. And then the middle branch is corresponding to this part. Okay? Okay. About this middle part. How do I draw it in the pull-up network? It shows up in series because these two parts are in parallel. Okay? The B is parallel to CD and E, so that's why it is in series to CD and E. Okay? And the CD and E themselves are, C is is in series to D and E, so that's why it's shown up in parallel. C in parallel with D and E. D and E are in series because they show up in parallel. Okay? If you want to write down an expression for the Y from the pull-up network, I'm going to write it down immediately, and you're allowed in any exam, you're allowed to draw it immediately. You do not have to do this. This is my own convention. It is not a convention worldwide. This is a convention worldwide. Whenever you write down this expression anywhere, you expect anybody to understand it as long as they understand digital logic circuits. But this is just my way of explanation. Okay? So let's write down the Y. We write it down as Y because it's a pull-up network. So I expect that the Y is equal to a 1. So I do not write it down as a Y bar. Okay? And then A has to be 1 in order for the Y to be connected to the VDD. Okay? So A has to be 1. How does A become a 1? It becomes a 1, this transistor becomes a 1 when this is 0. Because we want to have a potential difference here. And that's why it shows up as complemented. Okay? And then either this branch is 1, or this branch is 1, or this branch is 1. So this is why I expect to see an OR gate. Okay? And then an OR gate. And the final one is F bar, similar to the A bar. Okay? So what about these? In order for this branch to be 1, so this term corresponds to the middle branch being 1. How is the middle branch going to be 1? When this B is 1 and this part is on. Okay? So when this is on and this part is on. So B has to be on. How is B going to be on? When this B is equal to 0. Okay? Which means that it's going to show up as a 0. Okay, multiplied by a parenthesis which contains the C, D, and E. Okay, C or D and E. C or D and E. But do not forget the bar. Why bar? Because if I want this to be on, then this C has to be equal to 0. And this has to be equal to 0. And this has to be equal to 0 in order for these to be on. Each one of them to be on. Okay? Take De Morgan's law and apply it to get this result. Okay? Okay. Another final example. Before we take the opposite side of the game, the opposite side of the game, which is if you're given the equation and you want to write down the expression. Okay, this is a pull-up network. Okay, pull-up network. A and B. Okay, and this is its corresponding pull-down network. Okay, this is 2VDD. Okay, and for some reason I instead of feeding A to the gate, I'm going to feed A bar to the gate. Okay, so you know that before I do this complement, you know that A and A bar, you know that these two A's are connected together. But instead of writing down this wire, I just draw it like that. A and A. Okay? But for some reason I put here a NOT gate. Okay? So instead of feeding A, I fed A bar. Does it matter? It does not matter. Okay? So that's a NOT gate. How do we implement a NOT gate? By two MOS transistors. One PMOS and one NMOS. Okay? So instead of writing it this way, I'm going to write down A bar here. And it should be understood implicitly that there exists a NOT gate here. And I'm going to write down A bar here. Okay? If I write down A and A bar, if I forgot to complement one of them, that this would be a mistake. Okay? If I forgot to complement this A or that A, both of them have to be equal to each other. This is A bar, so this is A bar. If this is A, then this is A. But for this circuit, I decided to have A bar and A bar here, not A. Okay? So the question is, how do we write down the expression for Y? And I'm going to use the pull-up network to write down the expression for Y. If Y wants to be a 1, how is it going to be a 1 when it is connected to the VDD? So this has to be on, and this has to be on. Okay? So the QA, so let's do the same trick again. When QA is on, and QB is on. But this is QA bar here, because it's called A bar. Okay? Or let's even write down Q1 and Q2. This is transistor number 1, this is transistor number 2. Q1 has to be on and Q2 has to be on. Okay? So, when is Q1 on? Q1 is on when this input makes it on. Okay? How does this input make it on? When this input is opposite to the VDD, so there exists a potential difference between the gate and the source. Okay? How does there exist a potential difference when this is 0? So you want A bar to be 0. A bar to be equal to 0. So you want A to be equal to 1. Okay? So in order for this Q1 to be 1, in order for this to be on, A has to be 1. Okay? And this is why it shows up here as A. It does not show up as A bar. As opposed to previous examples. All of our previous example in this video, you found that A shows up as complemented. B shows up as complemented. C shows up as complemented. And this, it did show up as complemented in previous examples because we were feeding the A directly and the B directly. But this should not be always the case. This does not necessarily to be always the case. Okay? Sometimes I feed A bar. So in this example, I feed to the network, I feed it A bar instead of A. And this is why I do not expect A bar to appear, to show up in the expression, but I expect that A is going to show up in the expression. Okay? So A bar equals 0, A equals 1. So in order for Q1 to be on, A has to be 1. And how do I write A1, A equals 1 in the expression? I write it down as A. Okay? If I want A to be 0, then I write it down as A bar. Okay? Okay, but here it turns out that in order for this to be on, I need A equal to 1, so it is A. Okay, Q2. What is the value of Q? What is the value of B? In order for Q2 to be on, B has to be connected to the ground, so that there exists a potential difference here, and this potential difference makes this on, and thus Q2 becomes on. Okay? How is B going to be 0? If B is 0, then I write it down as B bar. Okay? And there's a multiplication here, so there is a multiplication here. Okay? Similarly, from the pull down network, y equals 0. When is y equal to 0? When this is on or this is on. Okay? When Q3 is on or Q4 is on. Because if both of them are off, then definitely we guarantee that this is not going to be connected to the ground. Okay? So, y bar. When is Q3 on? Q3 is on when A bar is equal to 1. Why? So that I can create a potential difference between the gate and the source. And this becomes an on transistor. Okay? So, this means that A equals 0, which means that A should show up as a complement. A0 shows up as A complement plus B, because this is going to be equal to 1, which shows up as B. Take the complement, y, A plus B multiplied by B bar. Okay? Take the complement and apply De Morgan's law. You end up having the same expression as above. Okay? So, to the final part of this video, where I'm going to teach you what if you were given an expression, a Boolean expression, a gate, a function, and you want to implement this function in terms of its as a function. You want to implement this function using the CMOS circuits. Okay. So what I'm going to have is that I'm going to give you this function. Y is equal to A bar B C plus A B bar C plus A B C bar. Okay? So this is the function that I need you to implement. Okay? So are we going to start with the pull-up or the pull-down network? We're going to start with the pull-up. Why? Because we're given Y or by Y or Y bar. We're given actually Y, not Y bar. If we were given Y bar equal to some number, then that would be a separate story. Okay? So it's much easier for us to implement it using the pull down. But here we're given Y, not Y bar. Okay? So we're going to implement the pull up network. Pull up network means connected up, connected to the VDD. Okay? Okay. What do I have? I have 3 terms ORed together. So if one of them gave me a 1, so you expect that the Y is going to be connected to 1. If any of these 3 terms gave me a 1, so I expect to have a 1. So that's why I expect them to be in parallel. Because if one of them gave me a 1, then I expect that the Y is equal to 1. If any of these 3 gave me a 1, then expect that the Y is going to be equal to 1. Okay? So let's study the first term. If the first term is 1, how can I implement the circuit such that this term becomes a 1? If I want A bar B and C to be 1, then I want A bar to be 1, B to be 1, and C to be 1. Okay, so all 3 of them have to be 1. which corresponds to having them in series. Okay, having them in series. Because if you connect them in parallel, okay, if you connect 3 transistors in parallel, then you expect that this is not going to implement this term. Why? Because if they're in parallel, then only one of them is sufficient for us to be 1. Okay? If only one of them is 1, then that is sufficient. But this is not the case here. This term is telling us that if I want this term to be 1, then all of them have to be 1. Okay? So I need to have them in series. Okay? So that if one of them becomes a 0, all of this branch fails. Okay? So let's connect them in series. Okay? Do not forget the bubble to indicate that it is a PMOS. Okay? The first one is A bar, the second one is B, the third one is C. Similarly, these 3 become in series. And all of them have to have a bubble. A, B bar, C. Okay? And finally, bubble, bubble, bubble. And this is A, this is B, and this is C bar. Okay? So, if you want to implement the pull-down network, what would you do? You take this and convert it to a pull-down network. Okay? Or if you want to implement it from the equation, you could take the complement of this equation and try to implement it. Okay? So I'm going to take another example on the pull-down network using another equation, which is not the pull-down network of this example. I'm going to take another example. Let me give you y bar equals A, B, C bar plus A plus B multiplied by C, and this here, we have a bar here. Okay? And let's write down a D here. Okay? Is this an equation for a pull down or a pull up? It's a pull down. Why? Because I have y bar here in the expression. Okay? So I expect to write down a pull down network. Okay? And the pull down network, at the end, I expect it to be connected to the ground. Okay? So the pull down network is connected to the ground. What do I have? I have 3 terms. And here I have the output y. Okay? When is y equal to 0? This y is going to be equal to 0 when it is connected to this network. Okay? So the y is going to be equal to 0 when this is 1, this is 1. Okay? Because when this is 1, then you expect y is equal to 0. So still, you are chasing the terms to be 1. It doesn't mean that y equals 0 means that you want this to be off. No, we're still chasing the ones. Whenever we talk about transistors, we talk about transistors being on. Because when they're being on, this will force the y to take the value of 0. Okay? Still, I'm looking, in order for this y to be 0, this term has to be on, or this term has to be on. Because when this term is on, okay, you expect to find a connection to the ground. And when this term is on, so you expect to find a connection to the ground. So you expect them to be in parallel. Okay? You expect them to be in parallel. Okay? So, how do we draw these 2 branches? The first branch is A, B, C bar. How can I guarantee that this A, B, C bar is to be 1? It is going to be 1 when A is 1, and B is 1, and C bar is 1. So these have to be connected in series. And thus connected to the ground. This is C bar, this is B, and this is A. Okay? So, what about the second branch? The second branch has to have two terms multiplied together. Multiplied together means that both of them have to be 1. Both of them have to be 1. So I expect to have two things in series. And then at the end, I expect to have something connected to the ground. What is the first thing? The first thing is A plus B bar, and the second thing is C plus D bar. So how do I let this term become 1? If this is 1 or this is 1. Okay, so either or means a branch. Okay. Oops, there's a mistake. I should not write down a bubble here, because this is the pull-down network. It's a pull-down network, so it has to be an NMOS. So this is NMOS as well. A plus B bar. If any of these is on, if any of these two transistors is on, then I expect that this is going to have a connection. But also I have to have C plus D bar. This term I have to have it on so that I can continue the connection to the ground. Okay? So again, two either or, which means that they are in series, and they are in parallel. This is the C and this is the D bar. Or you can write down the C and the D bar the opposite. This is the D bar and this is the C. It doesn't really matter. Okay? And this is the output Y. Okay? Okay, can we draw the output, the pull-up network from this example? Yes, we can. Let's draw it really quickly. Okay, we have two branches in parallel, so I expect to have them show up in series. Okay, I expect to have them show up in series. So so this is, of course, this is not the implementation of this equation, it's the implementation of the other equation. Okay, I expect them to show up in series. VDD. Okay, in series. That is the first one, and that is the second one. Okay, and then I expect to see Y. Okay, what is the first one? The first one has 3 in series, so I'm going to expect them to show up in parallel. And since we're drawing the pull-up network, so I expect to see a bubble at each gate. Okay, one of them is A, one of them is B, and the third one is C bar. Okay, these do not change, these match these. Okay, and then I need to see this part in series with that. This is in series, okay? But it contains two terms, two parts. The first one is in series with the other one. So I expect them to show in parallel. Okay? I expect them to show up in parallel. Okay? So this is like that in parallel. The first one is two transistors in parallel, so they show up in series. Okay, and the second one is two transistors in parallel, so they show up in series. bubble, bubble, this is D bar, and this is C. Bubble, bubble, this is A, B bar. A, B bar. And this becomes the equation. And this becomes the transistor. Okay? Want to write down the equation? You can write down the equation easily from this network, and it should map the De Morgan's law of this equation. So you take the complement of this equation, both sides, you expect to see the same equation. Okay? So these are the ideas of implementation of logic gates. You can pretty much apply these systematic steps to any transistor, to any equation that implements some logic gates and logic function, and they work pretty much similarly for all functions. And perhaps I'm going to make another video for how to calculate the dimension of these transistors to gain some properties. What is how do you calculate the time constant of these transistors? How do they perform? Are they good? Are they bad? And what is the power dissipation of these transistors? We haven't touched anything so far regarding these concepts: the power, the time, the area that it takes. So I'll keep stay tuned, and I'll post another video for that. Okay. If you have any questions, please let me know.